Okay, we have basically completed our energy level, and this is just information, right? Just in case you are interested to learn more about the physics involved, where is the application, right? We will learn about application later on, where we look at medical physics, and then we look at astronomy, where we apply what we learn in physics to the space. And this is one of them. We would have expect the spectrum of the sun to be white, but we see dark lines there, right? So dark lines shows that there is certain wavelength, and these dark lines show that certain element. Okay, so as the light is given out by the sun, it's continuous spectrum, but as it passes through these different elements, will absorb the different wavelength, depending on their depending on the element. So this one is just for info, right? For you are interested, you can read it up. You won't be tested, but in case you are interested in astronomy, right? So there are about today modern observation of sunlight can detect many thousands of lines, right? That's how we know what is present in the sun, right? Besides hydrogen, helium, and others. Okay, I think we have more or less completed. You can the Earth oxygen also lah. Some of the observed features are also caused by absorption in oxygen molecules in the Earth atmosphere. Okay, so for example, sodium absorbs some yellow light at wavelength of 5.89 and 10 to the power minus 7 meter. These absorbed color cause Fraunhofer lines. Fraunhofer lines are dark lines you see in the solar spectrum. By measuring precisely the wavelength of the missing colors, that is the Fraunhofer line, and how much light is actually absorbed, astronomers can learn much about the temperature inside the sun and chemical composition. Right? We will look into that later on in astronomy. Okay. Okay, let's go to worksheet. Hope we have managed to try some of them. Okay. Explain, very popular this one. Explain how a line emission spectrum leads to understanding that the existence of discrete electron energy levels in atom. Yep.
Yeah. Okay, I'm at the page.
Basically, each line corresponding to a specific wavelength or photon energy. A photon is emitted when electron changes its energy level. Since discrete energy changes, so discrete level. Okay. Any comment? Any question? Each line represents a wavelength. So wavelength represents a photon energy. There's
it's a very specific wavelength of light.
specific wavelength of light. So using E equals to HF, then we can say that it represents a specific photon energy. So it's photon energy, then it must be emitted by when the electron move from a higher energy level to a lower energy level. Okay or not?
Yes.
What does each line represent? This emission line spectrum. What
The
does
photon. The photon.
each line represent a wavelength,
Okay.
a single color, or wavelength, or energy of photon, no? Which color, blue or red, has a longer wavelength?
Red.
Okay. What does you observe? What do you observe about the lines?
Red is the most separator.
They are closer
Uh,
here,
the longer, yeah.
and then further apart at longer wavelength. Right? They are further, and the lines are further and further apart at longer wavelength. How is frequency related to wavelength?
F equals C over lambda. Inversely proportional.
Inversely proportional, or C equals to F lambda. Lo. You will see, you will use this formula quite common. Okay, which transition associated with atom energy levels is shown below, results in the longest wavelength radiation emitted? These two same answer lah.
E4. Wait, sorry. Uh, Longest wavelength.
Donkey, right? Wavelength is proportional to difference in energy level. Right? That different, delta E. So you want longest wavelength, delta E must be the smallest. So the smallest value is here, this one. But it's not given as a choice. So you have to choose alternate one, donkey. Donkey is E3 to E2. E3 to E2, this one. Okay.
Yeah.
For hydrogen energy level shown, answer the following question. What is the energy of the electromagnetic radiation emitted when electron move from energy level n equals to 4 to n equals to 2? Yep.
At n equals to 4.
Yeah, N4 is here.
Take the initial minus the final.
N2.
Uh,
So you can either take the large, that negative sign, negative 0.85 minus 3.40, or don't bother about the negative sign, just take the largest one minus the smallest one. Here,
E4 minus E2.
the answer is always positive, 2.55 electron volt. What is the wavelength? Yep. What is the wavelength?
HC over E.
Have you calculated out?
Uh,
You have to
Teacher,
convert
must I
it to,
memorize Planck's constant?
you have to convert this one to Joule first. right?
Teacher.
And then use this formula.
Teacher.
Okay or not?
Hello, teacher.
Yeah.
Must I memorize Planck's constant?
Then constant is given in the data sheet, so you don't need to worry.
Oh, okay.
Go to your data sheet. There's Planck constant. There's the speed of light. And take across there. Lambda 2.55, which is this one. Change it to joule. Right? 1 electron volt is 1.6 and 10 to the power 19 joule. And lambda. Then calculate your lambda. Which part of the electromagnetic spectrum is this one? Yep. Which part of the electromagnetic spectrum is this one? This is your AS work.
Yeah. Um, E is it? Okay.
Visible
Oh yeah. Okay.
visible Okay now, 400 to 700 nanometer or 4 to 7 and 10 to the power minus 7. Okay,
Yeah, visible light. Visible spectrum.
Balmer series is always visible spectrum lah. This one is infrared lah.
Okay.
For hydrogen energy level diagram shown, answer the following question. What is the ionization energy? Getting you to read the diagram. What is the ionization energy in joule? Yep. There, this one, the lowest one. The lowest energy level is ionization
Two.
energy,
Yeah.
13.6. Convert it to joule.
2.18 times 10 to the power negative 18 joule.
Okay. When electron make transition from energy level N4 to N3, N4 to N3, what is the wavelength of radiation emitted and which part of the electromagnetic spectrum is this radiation? Yep, what is the wavelength? Calculate out. Right? That's formula. Hc lambda delta E.
1.88 times 10 to the power negative 6.
Okay. Usually they give only two significant figure lah. So the answer is also two significant figure lah. Right off like 1.9 and 10 to the power minus 6 meter. So which part of the electromagnetic spectrum is this one?
Infrared, right?
Good. Infrared. Infrared. Okay. Let us try something. You can try the rest. I won't do all of them. What is the minimum excitation energy? That is from ground state to N2, right? Minimum, right? The electron is always in the ground state. So in order to be in the excited state, it must receive that minimum energy. Yeah. So what is the minimum? What is the minimum excitation energy that is from the ground state to N equals to 2? Which part of the spectrum is the electromagnetic radiation? Yep, yep.
Equals to 1 to n equals to 2.
Right, just subtract.
E got 10.2 EV.
10.3 electron volt. Ultraviolet. Okay? If you can memorize
Yeah,
that, 10.2 is the ultraviolet lah. Okay, the rest you can try yourself, but we will do one or two more. Okay. You can see very popular explain how the line spectrum of hydrogen provides evidence for the existence of discrete energy level in atoms. So memorize. So each line represents a photon of specific energy. A photon is emitted as a result of energy change of electron as it moves from higher energy level to lower energy level. A specific energy changes occur, so discrete levels. Okay, okay. Some electron energy levels in atomic hydrogen are illustrated in figure 7.1. Two possible transition A and B, giving rise to emission spectrum are shown. These electron transition cause light of wavelength 654 and 488 nanometer to be emitted. So these are in the visible region. On figure 5.7.1, draw an arrow to show a third possible transition. Yep, that should be the third transition. Transition means it changed from one energy level to another energy level. Yep, 1 mark. Just draw a line only.
Oh,
From here to here. Yeah, that's all. No others already. This one to here. This one to here.
okay.
This one to here. Calculate the wavelength of light for transition in one. Now, only should be able to do that. Just memorize the formula, that's all.
1.9 EV.
Right? Subtract to find the energy level, different energy level, convert it to joule, and then use this formula. Delta E lambda equals Hc. Right? There's your delta E lambda. There's your Planck's constant. There's your C. Okay, 1.9 times 10 to the power minus 6 meter. Light in a beam has a continuous spectrum of wavelength 400 nanometer to 700 nanometer. The light is incident on some cool hydrogen gas. Right? They show you in the figure. Using the value of wavelength in B, state and explain the appearance of the spectrum of emerging light. What do you see in here? In the emerging light. Right? You pass a continuous spectrum, 100 to 700 nanometer, to the cool hydrogen gas, and then you look at the emergent light. What do you see? Yep.
Dark lines.
What wavelength? These two wavelengths.
You mean? Oh, yeah.
This is the color. This in the region there. So you see this color, you won't see this one. Right? This one is in the infrared region. When you calculate it, you should be able to. This in the infrared region for this one. Spectrum appear as continuous spectrum crossed by dark lines. These two dark lines correspond to this wavelength, the wavelength given. Electron in gas absorb photon with energies equal to excitation energy. Light photon re-emitted in all directions, that's why you won't see them. They don't emit in one direction, they emit in all directions. Okay?
Mm.
I think that's about all. You can try the rest. Okay, we will. Okay, we watch a video, then we carry on.
Consider the Earth and a rocket ship which are bound together by gravity. If it takes work or energy to pull them apart, then the binding energy is the amount of energy it takes to completely separate them. Similarly, the binding energy in a nucleus is the amount of energy it takes to completely separate the protons and neutrons, collectively called nucleons. There are two forces acting inside the nucleus of atoms. The nuclear force, a residuum of the strong force that holds quarks together, is pulling the neutrons and the protons together, and the electric charge on the protons is pushing them apart. The strong force is a lot stronger than the electric force at short ranges up to 2.5 times the proton diameter. But at larger distances, the electric force dominates. So as we add nucleons and work our way up the chart of the periodic table, initially each nucleus is generally a little more tightly bound than the one before. This chart gives the actual numbers. This increase in binding energy continues until we get to iron and nickel, where the nucleus has about 60 nucleons in it. At this point, the nucleus has a radius more than 2.5 nucleons wide, which you remember is the range at which the repulsive electromagnetic force begins to dominate. So as we add nucleons past this point, the electric force trying to tear the nucleus apart starts winning, and each added nucleon is a little less tightly bound. When we get to lead and bismuth, and the nucleus contains 207 nucleons, the electric force wins, and the atomic nuclei larger than this are unstable and come apart by themselves, although it may take a while. These larger nuclei can return to more stable arrangements in several ways. They can convert neutrons into protons and give off beta radiation, or kick out whole groups of nucleons, 4 at a time, in alpha radiation. Or they can simply split into other smaller, more stable nuclei. When this happens, we call it fission. Fission is different from the other forms of decay because it can be harnessed and controlled via chain reaction.
This is fission.
Now let's consider what this means from an energy perspective. According to the binding energy chart, uranium has 7.6 MeV of binding energy for each nucleon, for a total of 1,786 MeV. While barium-144 has 8.3, and krypton-89 has 8.8. And the extra neutrons have no binding energy. So every time a nucleus of uranium fissions, we get about 192 MeV of energy. But U-235, left to its own devices, might take billions of years to decay. So we will want to help it along. We do this by shooting a slow neutron into it. It absorbs the neutron and briefly becomes U-236. Then it splits into krypton-92 and barium-141 and three free neutrons. Those three neutrons go to split other U-235 atoms into other daughters of more neutrons, and the process grows and repeats again. We can put the whole thing in water, and the daughter fragments and neutrons will be slowed by the water and cause it to heat up. Finally, we can use the steam to make electricity. This is how a nuclear power plant works. Ever since Einstein demonstrated the equivalence of mass and energy, physicists often give the rest mass of tiny particles like protons, neutrons, and electrons in units of energy. Two convenient energy units are the electron volt, or eV, and its cousin, million electron volts, or MeV. Using these units, here are some facts that will come in handy. The rest mass of the proton is 938.272 MeV. The rest mass of the neutron is 939.566 MeV. Let's take another look at the chart of binding energy of atomic nuclei. And now let's talk about fusion. If we can take a nuclei of deuterium, which has one proton and one neutron in its nucleus, and get it to fuse with a tritium nucleus, which has one proton and two neutrons, we would end up with helium, one extra neutron, and some energy. And we would have the basis for an energy-making machine. Let's run the numbers and see how it works. The binding energy for deuterium is about 2 MeV. And the binding energy for tritium is about 8 MeV. So the total for the input items is 10 MeV. The binding energy for helium is 28 MeV. And the free neutron has 0 binding energy. Subtracting the 10 MeV from the 28 MeV reveals that every time this fusion happens, we liberate 18 MeV of energy. And that's pretty good. But there's a problem. Getting the protons in the deuterium and the tritium close enough together so the nuclear force fuses them together is hard to do on Earth. This is the energy that powers the sun and the stars. But the sun's gravity holds the fuel in place, while the high temperature gives the nuclei enough speed to overcome the electric repulsion. If we could make a miniature star in the lab, a microsun, then we would be well on our way to having a great solution to our energy problems. And although this has proven difficult, significant progress continues to be made. similar to tritium, is an isotope of helium called helium-3. It could be substituted in the above reaction and would produce a similar amount of energy. What's the difference? Well, there's an estimated 1 million tons of easily mined helium-3 on the moon's surface. It would only take 25 tons to satisfy all the energy needs of the United States for an entire year. And 25 tons also happens to be the maximum payload of the space shuttle. And now you know why we're going back to the moon.
Okay, let us it's a summary for what we are going to do lah. Okay, let's make a start. We
Bro, I
let
find the video quite hard to understand.
say again.
I found the video quite hard to understand.
Never mind, we will go over that. It's a bit too soft. Okay. Under topic 23, nuclear physics, page 248, right, we go to mass defect and nuclear binding energy, radioactive decay, exponential nature of the decay, and define activity and decay constant, define half-life, right? That's a relationship between decay constant and half-life. And for mass defect, we look at nuclear fusion and nuclear fission. And then energy and mass relationship, E equals mc squared. Variation of binding energy per nucleon with A. You can use your own textbook. If you look at the mind map, we are just studying this part, that's all. Right? These are chemistry, studying chemistry, periodic table. You're not interested in that. Right, mass defect and binding energy. We'll define the mass defect and binding energy. Then sketch a graph of binding energy per nucleon. Apply the binding energy to nuclear reaction. Introduce Q value to tell whether the reaction is feasible. Application to fission and fusion. Okay, that's a syllabus. These are the data that we will be using. Okay, these are rest mass of proton, rest mass of electron, Avogadro's constant. Okay, relationship between mass and energy. Einstein suggests that energy and mass can be converted from one form to the other, as well as matter has mass. Right, so that's Einstein's relationship. E equals to mc squared. E is energy. M is mass. So that if there's a mass disappear, it becomes energy. C is the speed of light, 3 times 10 to the power 8 meter per second. The syllabus use delta M. Change in mass. You are required to recall and use. Supplying an object with any form of energy increases its mass. Energy and mass are equivalent, that's interchangeable. Right? do some calculation in worksheet where we calculate hitting an object and then calculate the mass that is received by the object. Law of conservation of energy and mass. Law of conservation of energy is now replaced by law of conservation of energy and mass. Total energy and mass is constant. Right? Previously was total energy is constant, but now total energy and mass is constant. Where mass disappears, it appears as energy, or likewise, when energy disappears, it appears as mass. Heating and mass increase. Heating an insulated block increases its mass. Right? It supply energy, so the mass must increase. Mass of moving body increases. So moving body, the mass must increase. But the increase is too small to be detected. So that's why we don't bother teaching you there's an increase in mass when you are hitting an object or hitting water. Atomic mass unit is based on carbon-12 scale. Carbon-12 has 6 protons and 6 neutrons. A sample of pure carbon-12 are much easier to obtain than pure hydrogen. Unit is used to measure mass of protons, neutrons, and electrons. Is the average mass of proton and neutron in the nucleus of carbon-12. Right? That's atomic mass unit. Either U or atomic mass unit. So definition, one atomic mass unit equals to 1/12 mass of an atom of carbon-12. Carbon-12 contains 6.03 times 10 to the power 23 atom. Mass of atom, we just divide, right? Change the gram to kilogram and then divide by 6.03 times 10 to the power 23. Right? So there's a mass of carbon atom. And there are 12 nucleons in carbon atom, so you divide by 12 to get atomic mass unit. Right? So that's given in the formula sheet. Okay, anytime we cut off, so you can try the worksheet while you wait for 50 minutes.
Okay.
Just a repetition, atomic mass unit is actually the average mass of a nucleon in carbon-12. Right? That's the electron. Later, an atomic mass unit. Right? It's convenient rather than every time write 10 to the power minus 31.